Welcome to NYU Tandon School of Engineering. I would like to start by asking you to consider Einstein's famous quote. The important thing is not to stop questioning. Curiosity has its own reason for existing. I think it's fair to say that each and every one of us here is because we are curious people. That's a good thing. Curiosity and intellectual hunger has led humankind to groundbreaking discoveries in science and technological advancements that previous generations could never have dreamed of. Today, we will be hearing about some of the boundary-pushing research being done by our speaker. This is the final event in the semester's seminar series in modern artificial intelligence, which I'm proud to say has become an important venue unifying scientific communities around the influential ideas of today that we predict will have a major impact tomorrow. Before I introduce today's speaker, I would like to thank Tandon's Department of Electrical and Computer Engineering for hosting the series, which we launched all the way back in 2017. Thanks as well to both Executive Dean Juan de Pablo, who also serves as NYU First Executive Dean for Global Science and Technology, and Senior Vice Dean Ray Odell for their steadfast support. Now, it's with great pleasure that I introduce Max Welling, a globally recognized leader in AI and machine learning. Max holds a full professorship and research chair at the University of Amsterdam, and he serves as American Distinguished Visiting Professor at Caltech. He's also the co-founder and chief AI officer of CuspAI, which focuses on AI-driven materials design. Max earned his PhD in theoretical high-energy physics from Utrecht University under Nobel laureate Gerard Hooft, and he transitioned to AI during his postdoctoral work at Caltech, and later with another Nobel laureate, Geoffrey Hinton. Max co-founded Skyfer, which was acquired by Qualcomm in 2017, and he has been a vice president and distinguished scientist at Microsoft Research. Max is one of the most cited AI researchers in the world, known for his pioneering work in generative models and variational autoencoders, which have influenced large language models. He co-founded Alice and served on the NERIPS advisory board, among other key roles. His numerous accolades include the ECE Conjuring Prize and Test of Time Awards at ICML and IPU. I know we are all eager to hear his presentation, which is intriguingly titled Transforming Scientific Innovation with AI. So without further ado, let's warmly welcome Max Welling.
Great, thank you very much, Anna, for inviting me here, and I'm very happy to be here. I changed the title a little bit, but it's exactly the same topic, so don't worry about it. I'll be talking about two concepts, two motives really today. The first motive is a theoretical one, and that is, I'm going to argue that there is a very deep connection between the topic called non-equilibrium thermodynamics and generative AI. So that's the theoretical thread. And then there is a very practical thread, which is how are we going to build a platform to design new materials, and in particular, to help solve some of humanity's biggest challenges, which are climate change, energy transition, health, etc. So let's first start with maybe the first sort of topic, the theoretical topic, the free energy. Now, what is free energy? I think even many physicists have different opinions about it, interestingly, because entropy, confusingly, is something that you can actually measure. But really, the way I think of it is a lack of information. So we have energy on the one hand of the free energy equation, which is our sort of maybe the total amount of energy in the system, but not all of the energy can be used to do useful work. In the Industrial Revolution, we sort of worked on the energy term, if you wish, and we replaced human labor by mechanized labor. We are now in the middle of an information revolution, or a digital revolution, or AI revolution, the way you want to call it. And you could argue that's related to the entropy term. And entropy, in my view, is a lack of tracking or a lack of knowledge or information about some of the microscopic degrees of freedom of a system. And if you don't have these degrees, if you don't know about these degrees of freedom, you cannot leverage maximally the energy in the system to perform useful work. You can still do work, You can build a steam engine from the heat or something like that, but it's quite inefficient. And therefore, entropy is actually somewhat of a subjective sort of notion, in the sense that if you were all-knowing, omniscient, then you would know where every microscopic degree of freedom in the world is. You wouldn't have any entropy term in your equations. It would just be, Hamilton's equations, which would be evolving over time. So in other words, it really represents our lack of information, and that's very similar to what we have in AI. In AI, we introduce probability distributions to represent the lack of knowledge we have about the details of the system. Okay, so then about the second motive in this talk, this is about climate change. So these are the carbon dioxide levels in our atmosphere. And you can very nicely see that, when the steam engine was invented, these levels were going up. This is my birth year. Not like I want you to know precisely how old I am, but I do want to let you know that it's my generation that profited most from the ability to pump carbon dioxide into a shared resource, our atmosphere, without paying for it in some sense. But as we all know now, that causes global warming, and there is about a few years left of atmosphere, if you wish, to put carbon dioxide in, because after that we'll start to hit 1.5, 2 degrees global warming, and that will have all sorts of negative consequences and possibly irreversible tipping points. So my point is that it's our generation that also should feel the kind of responsibility to do something about this. Now you could argue, we should just stop emitting, or we should, make sure we quickly get onto renewable energy, and I agree with all of that. We should stop emitting and quickly transfer to renewable energy. The only problem is that under every possible scenario that people have agreed on, in 2015, we should then be carbon neutral, which means the amount of carbon going into the atmosphere and the carbon that needs to come out of it needs to be balanced. But then, if you look at these curves, these are IPCC curves, so they go to the right and they go negative. This means that we still need a century of negative carbon emissions, meaning we have to remove carbon enough from the atmosphere, not from a smokestack or by not emitting. All these solutions don't work anymore. We have to get it out of the atmosphere. And I'll argue that in a minute that that's actually very hard. And that has to happen at about half the rate that we are emitting now. So we're currently emitting about 40 gigatons a year. We need to, per century, get about 20 gigatons out of the atmosphere annually, and that's a Herculean endeavor. So to come back to free energies, then, it turns out, this is actually very cute, I find, you can compute an absolute minimum of work that you need to perform in order to remove carbon dioxide from the atmosphere. So we know the dilution is about 0.04% of carbon dioxide in the atmosphere. And there is a second law of thermodynamics that says that the amount of work you need to put in is lower bounded by the change in free energy between the initial state and the final state of the system. So the initial state of the system is, like this, which is, these are all kind of molecules in the atmosphere, and the red dots are the carbon dioxide molecules. That's the initial state. The final state we need to get to is something like this, where the carbon dioxide is separated in a separate chamber, and that chamber should probably be some cavity, below the Earth, where we pump the carbon dioxide in, and so it's contained there. And now the amazing thing about thermodynamics is that in order to compute the amount of physical work you need to put in, can be computed by a combinatorial argument, an information argument. So this is an information state, which is higher, more structure, there's more information, you know more about the world in this state than in this state, because you separate the two gases. And from that, you can just compute, how many possible states can the world be in here, how many possible states can the world be in this case, and that difference, the log, etc., will give you the actual, multiplied by the temperature, will give you the actual work that you minimally have to do in order to achieve this separation, and there's no escaping this second law. So now if you look at the case of, if you plot as a fraction of the amount of carbon dioxide in the atmosphere, the amount of megajoules you have to put in for every ton of carbon dioxide you want to pull out of the atmosphere. This is the curve. So at actual dilution of the atmosphere, you're looking at about 550 to 600 megajoules per ton. It's very large. Of course, if you go to a smokestack, you're more like here. So that's much more efficient. So please do it now when we are emitting it. It's much better to do it at a smokestack or not emit at all. That's even better. But as I argued, you might not be able to avoid the issue. Now, in the best case scenario, that amounts to about 5% of our current energy use to be then used to pull carbon out of, using DAC to pull it out of the atmosphere. That is the absolute minimum. It's more something like 50%, 10 times as much, due to all the inefficiencies in the process. So that's a huge amount. Now, 5% doesn't look so bad, maybe, because we are about to use 5% of our global energy use on AI. So why not use that same amount on fixing the planet for the future generations? So it doesn't seem so bad. But 50% obviously looks a lot worse than that. Now, if I look at this, you could just say you give up, right? Or you can fight. And so what can we do to try to improve the situation? Well, the first one is energy price is the biggest thing we need to get down. So if we can get the price of energy down, this will be super helpful. The second thing to do is to improve our sorbent materials, the materials to which the carbon dioxide is sort of attaching, binding, and from which we also need to regenerate it, so unbind it and put it in the container. So we can shave off 30% of this number by improving our sorbents, and so that is what so that's why I started this startup, CuspAI. It's not just for carbon dioxide. We also work at batteries and clean water and all sorts of other interesting use cases. But we also have a project in carbon dioxide removal. And so what we're doing is we're building a platform to accelerate the discovery of new materials with desired properties as fast as possible. So usually this is like a decade-long process to figure out new materials. It's basically a whole bunch of physicists and chemists sitting in a room talking, doing experiments, and then talking again and doing experiments again. So the point is that many of those kind of experiments, the information that's coming out of these experiments can already be predicted in a computer. So the more we can do in a computer, the less experiment we have to do, the faster the innovation cycle happens. Okay, so what does the platform look like in broad strokes, of course? The first thing here is generative models. So these are models that try to do the inverse problem in one shot. So they say, the forward problem is I give you a molecule, you tell me what properties it has. The inverse problem is I give you the properties, give me a molecule with those properties. That's the inverse problem. Now, if you want to solve the inverse problem in one shot, you basically have to have a model where you prompt it, like a search engine, you type, I want a molecule with these properties, and it will generate a list of 100 molecules which have these properties. Now, that sounds too good to be true, and of course it is. And the only reason we can at least approximate that is we are doing a lot of work up front in evaluating many molecules and their properties. And instead of throwing that information away, we are storing it in models. And from that information, or if you wish, the energy we have invested in that calculations, we can now actually build generative models. That's basically a summary of everything we have seen before. But they will never really solve the problem, I don't think. That would be real magic. So there's other things we need. So once molecules or candidates have been generated, then they go to what we call the evaluation stack. And this is crucially a multi-fidelity evaluation stack. So this means there's very cheap, fast property predictors in there to throw out everything that is clearly uninteresting. And we need uncertainty prediction, as I will say, and I'll talk about a little bit more, because you need to know if you throw something out, you need to be pretty certain it's bad. Otherwise, you're throwing out possibly good candidates. And then you go up the stack. So you sort of move to the next ladder, which is a slightly less efficient but more accurate, and then a slightly more accurate. And then all the way up there, you're going to very expensive quantum chemistry calculations, and then you escalate to an actual experiment, which is the slowest and most expensive thing to do, but sort of closest to the ground truth. And building that multi-fidelity stack is really key, in my view. And of course, there has to be an agent that orchestrates all these calculations. At what level of the stack should I do an evaluation? Should I use a GPU or should I use a CPU, right? All these kinds of decisions have to be made by this agent, and this you can call this a search agent. And it also has to decide when to retrain the model, because every time we do calculations on this evaluation stack, we are generating data. And that data is useful data for all the less accurate models that are sitting below it. That data gets stored in a database, and the agent so now and then decides, okay, we should retrain this model and retrain that model. And as we are retraining these models, the search process becomes more and more efficient. So that's a flywheel that will start to run faster and faster and faster, and hopefully more and more of the work will actually be done by the generative model. In the ideal case, you type an answer, the generative model gives you a material and it works. It's an ideal situation, but that would only happen after many rounds of using the platform, I would say. Okay, so now back to the other motive, the motive on generative models and its relation to thermodynamics. So this one on the left-hand side is the variation autoencoder, which Dirk Kingman and I introduced in 2013. So pictorially, what happens is there is a data distribution, QD. So here is the data distribution. It's supposed to be complicated, to manifold. We take a point, we push it through an encoder. Now, the encoder is a neural network that predicts the mean and the variance of a Gaussian distribution. And then we sample a point from that Gaussian distribution. But most of the work is done by a deterministic neural network, and it's trainable. So then if you push all the data through this encoder, you get a distribution, what we call the aggregated posterior distribution in the latent space. And it's designed to be a simple distribution, although it's not always. It is a simple distribution designed to be a simple distribution. It looks maybe like a Gaussian. Assuming it is a Gaussian, and there is a decoder where we pick from this Gaussian distribution a random point. You can think of it as a random number, a code. And then you push it through an inverse of the encoder, the decoder, that then tries to bring that point and project it back onto the data manifold. Okay, and so you have sort of these two should be each other's probabilistic inverses, and you can write down something which I will explain looks like a free energy to minimize in order to train both of these models, encoder and decoder. Now, in all honesty, it was a kind of a nice idea, but it didn't generate very crisp, nice, beautiful images. And people want crisp, nice, beautiful images. So then along came this paper. It's hard to read, but it says deep unsupervised learning using non-equilibrium thermodynamics. And it's by Usher, Soldixstein, and collaborators. So what did they change in this architecture? What they changed is they kept the encoder fixed. It's just an Ornstein-Uhlenbeck process. And they introduced very many stochastic layers. So it's like instead of a deterministic map and then a Gaussian, they did many stochastic layers. And then every time you take a little step, you monitor what happened. And then you try to invert it. You try to undo it in the other direction. You train a model that undoes this kind of forward model. And so here you have a data point, and you can track it. And so the entire data distribution sort of fuzzes up into a fuzzy ball of a Gaussian distribution. And your task is to build basically a vector field, if you wish, that takes a point and guides it back onto the manifold. Okay. Now, I want to point out again that especially this process is a thermodynamic process. In particular, this process is a process where entropy increases. Now, you might wonder, well, why does entropy increase? Points just get mapped to points. But the idea is that you're losing track. This is perfect mixing of these points. So points which are close here are now arbitrarily mixed in this space. So you're losing track of the information of where the points are. So they go from a structured to an unstructured space. If you describe this with thermodynamics, you have a system that increases entropy, but doesn't do any work. It just relaxes. Unfortunately, this is the fate of everybody and everything in this universe. If you don't do anything, you'll just become a fuzzy ball of atoms. Now, the inverse of that is actually something that goes against the law of thermodynamics. So in other words, it is the proverbial omelet that turns into an egg, right? So here's the omelet and here's the egg. And that's a system that reduces entropy, which is not possible in the real world. And therefore, well, it is possible if you perform work on the system. And of course, that is, you will create more entropy somewhere else. But in this particular case, if you perform work on the system, you can reduce the entropy. And where is the work being generated? Well, you're computing score functions, which is basically forces on every point. And those forces drag you to the manifold. That force performs work. And it's literally physics, right? So it's kind of interesting. And of course, the authors already knew, right? Because they said non-equilibrium thermodynamics. So it didn't come as a surprise to them, but I think it's really much sort of emphasized. So to take this a little bit further, I'm going to argue that these two fields are actually, the mathematics of these two is actually just the same. And maybe that's not surprising for some because there's an underlying node, which is information theory. Information theory is both the underlying theory for machine learning, and as many physicists will tell you, it is also the underlying theory for much of the physics that we see. Okay, so thermodynamics, we have a Boltzmann distribution. That's the equilibrium distribution over microscopic degrees of freedom that we don't track, given macroscopic observations. These could be temperature, volume, pressure, whatever you're measuring. And then that distribution looks like this. So e to the minus Hamiltonian, which is the energy function that drives the microscopic dynamics over temperature, and then divided by a partition function. Now you can define the free energy in equilibrium statistics. That is just the minus t log partition function. But you can, that thing is upper bounded by a variational free energy, which is a free energy which is also valid out of equilibrium. And that is the expectation under Q of the Hamiltonian minus T times the entropy of that Q. So if you relax a system, basically you do steepest functional descent on this object. It's called, has a name, anyway, I forgot the name. So there's it is steepest descent over Q on that functional of Q. And that's actually how physics evolves. So relaxation of the variational free energy over Q is the equivalent of a relaxing system that increases entropy and it generates heat and gives it to the environment. Now changing H, which is change the physical system. So there could be all sorts of parameters in H. Now you're changing the physical system. Is actually the equivalent of performing work. And if you read books about stochastic thermodynamics, you'll find that these definitions are exactly the way that people define work and heat in stochastic thermodynamics. Now to machine learning. In machine learning, we have a posterior distribution. Again, there is a whole bunch of degrees of freedom that we don't wish to track. I mean, you're driving a car and there's also things happening around you, including other cars. Keeping track of all these degrees of freedom, you have some probability distribution over what's happening around you. And so we are interested in the posterior distribution of all the things that we don't keep track of, given the data, which is the things we know. And of course, by Bayes' law, we know that that's equal to this. So then in machine learning, we have defined what's called the evidence lower bound, or ELBO. And that's the negative of a free energy. And it was already Radford Neal and Jeffrey Hinton, which in the 80s actually already defined this free energy. Literally like this. So the free energy, again, the equivalent of the equilibrium free energy is minus log marginal, which is the thing you actually want to make small, because that means your data have high probability. And that is lower bounded by the variational free energy, which is the expectation over minus log the joint minus the entropy of Q. And you can just derive this, and then you compare, you see that the energy is equal to the minus log P of the joint. And there's a famous algorithm, which is called the EM algorithm, where you learn models on data. There's the E step, where you minimize this variational free energy over Q. And that is now equivalent to a relaxing system that generates heat and then increases entropy. And there's a learning step called the M step, which minimizes F over P. And that is performing work on the system. So learning is performing work. And that makes some sense, right? In order to learn something, we need to create structure in our brains. We need to reduce entropy. And that is cost energy, and that's performing work. Okay, now with that theory in the back of our minds, we can set to work. We can generate from noise beautiful images using the diffusion model, again going against the law of thermodynamics, or beautiful videos of dogs playing in the snow, which is all extremely cute and lovely to look at. But to do something truly useful, you can also use it to generate molecules. Right, so here's an old paper, not old, well, I don't know, maybe 5 years old or something, 10 years old, where we use equivariant model to predict, to generate molecular structures out of noise. And this is a somewhat later paper where we used the same technology to generate drug-like molecules that fit in the pocket of a protein, and so they can be a drug for disease, for instance. And you can use it to generate metal organic frameworks to capture carbon from the atmosphere. So we build a autoregressive generative model that generates these beautiful nanoporous structures. And we've generated millions of these by now. And then, of course, they go through our evaluation funnel in order to find the ones which are best for a carbon capture application. Okay, so just give you an overview of where free energy and these concepts that I've been talking about, how they relate to machine learning concepts. So I've talked about it. There's two things you need to know in terms of ingredients. You need some kind of free energy, or KL, which I've written down before, which is this. And then you need Markov chains. So we need a forward Markov chain, which is the physical Markov chain, which increases entropy. And then there's a backward Markov chain, which turns the omelet in an egg, which is unphysical. And it starts at basically a noise distribution and works its way back to the data manifold. And now it turns out that all of these things that we do in machine learning are describable by a very simple formalism. MCMC sampling is a chain like this, where we design the forward kernel such that we sample from the correct distribution. Variational inference is literally this. Diffusion models is when we have data for Q0, and we train a model that goes from noise, by backward transitions to generate, data that is like Q0. Normalizing flows are the deterministic version of this. And we have RL and stochastic optimal control, where again we have something like this. Actually, more something like this, where we now have a reward function. So we don't have data, but we have an actual target distribution, like in MCMC, from which we want to sample. Let's say this one is a target distribution. That is an encoding of your rewards. And we train a stochastic model to basically sample from that distribution. So we train a policy to make sure that we are acting in such a way that we reach that distribution. And finally, there's Schrodinger bridges and optimal transport. They're being used a lot in machine learning, but they're more mathematical concepts that also fall very beautifully in this framework, where in Schrodinger bridges, you compute an optimal strategy to go from one distribution to another distribution. With stochastic transitions in optimal transport, you do the same, but just with deterministic transitions. And I write a book about this, and it's to remind myself that I can finish it, but hopefully in the summer there will be something online. Okay, so the second part of the stack that we are building is this evaluation stack. And this strategy or the philosophy here is to go from simulation to emulation. So simulation is the expensive physical simulation where you need to follow the laws of physics. Emulation is where you try to predict what the simulation would have given you, but with machine learning models. And these could go all the way from direct property predictors to faster ways to simulate. So let's say you are working in a lab and you found a nice molecule that you love, and you're starting to sort of simulate it in your computer to figure out what the properties of that molecule are. So it's expensive, you need to invest a lot of energy and capital to do it. And then, but it didn't do what you actually wanted to do, so you sit down again, you come up with a new molecule, and you do the simulation again, right? And so hopefully it's better. But you now basically twice use that amount of energy. A better way, this trick of amortization, is to save all of these simulations, put them in a big database, then train a property predictor or machine learning force field or anything like that, that helps you speed up the simulation next time around. Right? You could just predict the outcome directly, or you could just predict all the forces instead of doing quantum computations, and you can accelerate that simulation process. So that's the idea of emulation and of this multi-fidelity stack, but also this idea of improving the use of and accelerating this as we go and generate data. And so I just want to point out that this idea of this evaluation stack has already been on chemists and physicists' minds. So the physicists know very well, that there is a range of simulation tools and different levels of granularity that you can deploy in order to analyze a particular material. So if you're interested in a single molecule and maybe a reasonable number of electrons, you can actually try to solve the Schrödinger equation itself. It's very expensive, but if the system is small enough, you can do it, and it's of course very accurate. But if you're interested in a bigger system, you need to go up this ladder. So density functional theory. You can do now thousands of atoms. And you can go to atomistic and molecular simulations, which you can see here. This is a Langevin equation. Change in the position is a velocity, and the change in the velocity is given by this term, friction term, noise term, and a force term. The force term is given by quantum mechanics, but you can replace it with a machine learning neural network. You can go up, you can start to coarse grain particle-based methods, coarse grain particle simulations, all the way up to classical density functional theory, which we have here, and continuum methods, which are PDEs. Now, for each one of those, there is a machine learning surrogate version of that, all the way down to quantum neural Monte Carlo, quantum DFT functionals, force fields, and then these simulations. You go all the way up, and you get like these modern weather prediction systems like Aurora or GraphCast or ForecastNet or Pungo Weather. They're all machine learning methods to predict the outcome of the Navier-Stokes equation. And I'll talk a little bit about a method we have been involved in to describe liquids and soft matter with a learned functional. So one word about force fields. So the updates that you need to track are these. So it's just Newtonian mechanics, very easy. Conditions velocity, change velocity is force. These forces are unfortunately quantum mechanical, and also the trajectory is highly chaotic. So it's a very hard problem actually to simulate. And so these force fields have started to occupy the space between ab initio, very accurate quantum mechanical simulations on small molecules, and classical force fields for much larger systems. The machine learning force field can get close to the accuracy of the quantum mechanical DFT calculations, and can treat systems which are as large as the classical force fields can do. And so we worked on that as a bunch of papers. We've made these force fields equivariant so that they understand that if you rotate the world, actually nothing changed. So if you translate the molecule, nothing changed. So you need to tell, unfortunately, these systems that that's the case. They don't understand it completely, automatically, and so that's where this equivariance came in. Here's another interesting application area. This is called grand canonical Monte Carlo sampling. And that system, you need the simulation tool you need in order to compute how well does, let's say, carbon dioxide stick to the the surface of a nanoporous material. So what you do is you pop in molecules randomly, insert them or delete them randomly, and then you wiggle them around a little bit, and you see if they stick to the side. And you do this under different pressures and different temperatures, and then you trace out the so-called isotherms as a function of pressure. And these tell you all you need to know in order to evaluate how a molecule like that would behave in a carbon capture machine. And so accelerating this is actually important, and we're working on accelerating this on GPUs in collaboration with a large company, and we open source that. But it begs the question, can we do this faster? Because this takes at least a day and sometimes a week in order to compute these isotherms. It's very expensive. And that is a bottleneck in trying to search through many, many materials. So how can we accelerate this? So here's a way that hasn't, so this is at my university work, this is not yet at CUSP. And that's a variational free energy approach. So again, it's back to free energies and back to variational systems. If you know something about physics, then this is the grand canonical potential. This is the potential that where the magnitude of the density rho tells you how many molecules are at a particular. There is a term here, which is the internal free energy, which models all the internal dynamics of the molecules. And then there is the interaction with the liquid and the external potentials. And there's a chemical potential. And the idea is so the physicists couldn't really they couldn't write down a good functional F. It was very hard. They've written down a few of them, but it didn't really result in a good accurate method. And that's why this classical density function theory is actually not used very well, and very much. But it's a huge opportunity because we can learn this functionally using machine learning methods, and then it might become useful. Okay. I feel this might be a little too technical, so I'm going to skip over this. But we have developed a method which we published in PRL that can train these functionals very effectively just from bulk material. So you don't even have to have different potentials. You just set potential to 0. This method, based on MD simulations, can actually train a model that can then be used to, let's say, relax the system to equilibrium. So here's the ground truth equilibrium system. And the blue line is basically the self-consistency iteration, similar to quantum DFT, where you relax the system to its equilibrium state. And now it's actually very successful, I would say. So you can then stick that into a dynamical equation, the Fokker-Planck equation, which tells you how liquids behave in the overdamped limit, in this case, when you try to relax them, when you let them relax. And you can use exactly the same grand canonical potential here. You stick it in the Fokker-Planck equation, and then you can let it relax. So now it's a dynamical system that tells you how does a system relax to equilibrium. And it tracks the actual Brownian motion very well, but the Brownian motion is an MC sampler that takes at least a day to simulate, where our system is done in a few seconds or under a minute or something. So a huge acceleration potentially. And then you can use that in the setup where you can actually look at things like breakthrough curves. So these are systems where on the one end you have there's a wall here, there's a high pressure gas, and it wants to break out. And then you remove the wall, right? And then there is these potentials. There are two different potentials, the blue and the red one. You see two curves. And the gas tries to go to the right-hand side because here's a low pressure sink. It tries to go to the right-hand side. Whenever it hits this part, the curve on the right will start to rise. And that's what's called the breakthrough point. And then in the end, it will have to go to 1 because the amount of stuff that comes out here and the amount of stuff that goes in here needs to become an equilibrium. That's a steady state solution. So if you do that, and you see the dashed curves are the very expensive MD simulation, the solid curves are the very fast variational system, and it is just slack on top of it, right? So it's very nice because you can now do these things which you can actually measure these breakthroughs of curves. You can now do these things in your computer very fast, and that will speed up the search pipeline. Okay, so the last topic I want to talk about is uncertainty quantification. So I argue that we need this multi-fidelity stack. And in order to build it, in order to understand which materials you can confidently dispose of, you need to understand how certain your predictions are. And so with Dario here, we've started a program in uncertainty quantification that is faster than just doing a whole bunch of simulations with slightly different initial conditions, because that's slow, right? That just scales with the number of those lines that you have to compute. And I'll just don't go into too many details, but here's 2 examples of autoregressive problems. We're not actually applying this to force fields directly, but these are for autoregressive problems. Of course, the future prediction of solving of a PDE is an autoregressive problem. You to try to predict the next state of the PDE given the current state, and also a sort of neural, generative model for molecules. Molecules can be represented as smile strings, and you can think of this as a language model where you sort of generate each symbol or token at a time in an autoregressive way. But these are 2 problems that are autoregressive, and the way we solve it is by variational Bayes again. The same idea. Now we write down the elbow, but we write it in parameter space because we're Bayesian, so we write down free energy in parameter space. And we are basically saying, well, if this is the true posterior, we are proposing that there is a sort of a tractable family of distributions that we try to get as close as possible to the blue line, and by minimizing this elbow. And sort of here's the idea. So you have a mean forecast and you have a real-time series, and then what we require from the system is that the blue band of uncertainty captures the variation between the forecast that we are given and the real outcome of an experiment. And that's what we call BARN for a Bayesian autoregressive recurrent neural net. So here's the idea of BARN. So there's a prior model, like it's very much like a VAE type thing, but now over time series. So there is a prior model. The prior model has transitions in observation space. So these could be, the weather states, let's say, of the model, or it could be the individual tokens of the molecule. So if there's a transition model that takes you from, from a state to a next state, given a bunch of parameters. Now, if the parameters were fixed at every point in time, then it wouldn't be Bayesian. So we need to sample them from a prior distribution. The prior distribution over parameters which we sample from, and then we use to parameterize this transition probability. Okay, that's the prior. The posterior distribution is a variation of posterior, where instead of sampling these parameters from a prior, we are now sampling it from a model that looks at the past. So it looks at all the past states, and it's a neural network that then predicts, the next parameter set given the previous states. So that's the posterior. We train that in the usual variation way. And so that's hopefully now, a good model for Bayesian uncertainty. So again, we look at 2 problems here in more detail. The transition probability for the PDE solver is given by a model for the mean. So the mean for the Gaussian distribution at the next time step is given by some model that depends on the previous state and the parameters. There's a fixed uncertainty. The model for the smile strings for the molecules is now the transition probability now depends on all the previous states and parts of the parameters. It's a softmax of a latent state H or a hidden state H at the previous state, but the previous H is now given by an RNN, a recurrent neural network of the previous observation and the previous hidden state HT-1. And because ht minus 1 again depends on ht, minus 2, etc. You end up depending on the entire sequence of observations in the past through this deterministic RNN. Okay, so then this is an actual simulation for the system. So the blue line is what we predict. The red line is the actual CDF solver, and the uncertainty band is what it thinks the uncertainty ought to be. And so we really want the dashed red line to be within the blue band. And so you can see that as it becomes more uncertain and starts to deviate from the actual ground truth, it understands that it is deviating from the ground truth, and it's increasing its uncertainty as it goes. Now, there's a number of, of course, a lot of experiments that we ran. So the most important thing, the conclusion from these, curves and tables are that we do get much better calibration than other methods, like there's ARD, automatic relevance determination, dropout, perturb, refiner. These are all methods that claim to, do uncertainty prediction. And so, we get much better calibration, also these curves. But not only that, we also get much better predictions. And that's kind of an interesting thing. So somehow this uncertainty also helps you make better predictions. So this is just looking at the molecular strings. And you can see, especially for the long dependencies, like if you have a ring, you open a bracket and then you do a whole bunch of stuff. You have to close a bracket. So the long-term dependencies, they are very well modeled by this Barn model. So it's actually good at both the prediction part as well as the uncertainty calibration part. For instance, on these molecules, it's better than SMILE's LSTM, which is specifically trained on, is an LSM specifically trained on small strings. And Barn beats it well. Okay, so then we're coming to the end. Somewhat sort of dramatically, we have named the ages in which humanity lived, or the progress that we've made after the materials. Now we think we live in the AI age, but I would actually think that below that there's always a material challenge, right? Because what drives AI is the materials problem, silicon, right? So there's materials are really important, and are at the root of many things. I think with a good search engine and lots of AI, we can get to an age where we have precision materials on demand. So you use a search engine over hypothetical materials. You ask for a material, and it will generate for you the material with those properties. And then you order it by Amazon, and then it will be dropped by a drone on your doorstep. That's the future. And the reason why I think this is a good time to work on this is that we have the molecular sciences, which have become very advanced. The computational sciences are now mixed in with AI, supercomputing, and quantum computing in the future. But maybe most importantly, the applications are pooling, and there's a need for these things to develop because we want better healthcare solutions, better drug, better vaccines, better antibiotics, better cancer medication, all these kinds of things. But we also want better energy solutions, better battery, fuel cells, synthetic fuel, carbon capture. We want all these things are material problems, and we want better semiconductors as well, actually. And that's the field, I would say, of AI for science, which is really gaining a huge amount of momentum. In fact, in spring, I'm involved, and Jan Cohen is also involved in an entirely new conference on AI for science, which will happen, I think, at Princeton. Okay, so what I've argued is there is a deep relationship between non-equilibrium thermodynamics and machine learning, and the name of that relation is the free energy. That's the bridge between them. I would say we are building a new superpower for science, which is AI or data science, however you want to call it. And we should make the best of it. And I would say these new tools can really help us at least make progress in some of humanity's largest societal problems. And these days, we have to do it with our politicians. They're not really helping it, at least not in climate change. And so technology will have to advance the state of the art here, I think, and help us. Okay, this is the team at CUSP. And besides, so I've already shown you the pictures of the students. This is the team at CuspAI that is working on the platform. And I'm very happy to take any questions.
Start with a question. So this pipeline, when you're saying you're developing materials for trapping CO2, and then you're going to external companies that evaluate the process, right? That evaluate.
Yeah.
How long does this entire pipeline and how much effort it is in terms of computations to evaluate your designs?
Right. Okay, so the pipeline we are building for carbon capture is designed to be 6 months. And in those 6 months, there's about 4 months of designing and internally evaluating. So this includes computing these isotherms. We have a process model where we stick the isotherms in the process model, and it evaluates how well we predict this material would do in the real world. Then it goes to a synthesis partner. So the synthesis partner has given us the specs for what they can generate and what they cannot generate. Those constraints go into our generative models. So the only things we generate are things that they can actually synthesize. And they can actually scale it up to ton level, not just kilograms, but they can go all the way to ton, which is important if you ever want to really use it. Then that company also characterizes the material and first by crystal X-ray kind of thing, so that you make sure that you understand a bit what the structure is. And then it goes to an actual carbon capture partner that takes the material and puts it in an actual carbon capture machine, and start doing tests on how well this material works as a carbon capture material. All of that happens in about 6 months. We are in month 4 and we are 1 week behind. That's the status of that project.
So it seems like an important thing here is like somehow formally encoding these specifications of what can be produced, like what molecules can be produced. Is that a challenging process? Like what is the form, like what would be an example of a specification of that form?
Okay, so let's do metal organic frameworks, right? These are these beautiful, you get back to that thing. This one, right? So the way to specify one of these is to break this molecule up into linkers and nodes. The nodes are typically metal nodes, but these days they also put other things in the node. So you think of it as a graph or a net, that's what they call it, with no vertices and edges. The edges are linkers, and there's just a large library of linkers around that people have already synthesized.
Okay.
But you can definitely also generate your own linkers, and people have built models to generate linkers. And then there is a library of a much smaller library of metal nodes, because metals are harder to get, and certain metals you just simply don't want because they're too expensive, or they come out of dirty mines or whatever. So there's a much smaller set of those metal nodes. And then there's the rest is combinatorics in this particular generative model. So you come up with a generative model to combine these things with certain probabilities. It's autoregressive, and once you have the pieces, you then have some process in which you sort of relax that and sort of put it together. Now there's other models like MockDiff with the paper, where instead of doing that autoregressively, you can do it by diffusion. So you basically have you sort of generate, you could generate metal nodes, you can generate linkers, and then you can generate a combination of those in a net. So that's a hierarchical way to generate things. So to come back to your question, the specification in this case really is kind of the building blocks.
Like a list of building blocks you can use.
And then of course you need enough data for each one of the building blocks in order for this model to understand what to generate. If the models are small enough, you don't need a specification. The specification is basically the atoms. The atoms and the type of atom. That's all you need. And their position. But of course, it's more like the distances between the atoms. It's called a CIV file. So that's basically precisely how you specify a particular molecule. But if they get bigger and bigger, like if it's a crystal, you also have, of course, the unit cells. So you want to also figure out, what are the the directions of the unit cell. And within that, you have to put the atoms, and then they repeat over the unit cell, right? Over many unit cells. So that's a slightly different representation for crystals. And so, yeah, but not super complicated.
Any more questions?
So, someone else has one.
Yes. So can I ask that, is there any materials you have already applied for real world manufacturing?
Yeah, so this stuff here, the metal organic frameworks, we have generated, and they're, I think this week they're being shipped to the synthesis part.
I have a question. So like was there another one behind me?
There is somebody that's.
Yeah,
Someone else is new. Yeah, you asked. Go ahead.
Yeah, I was just wondering, so this was a very interesting talk, and you talked mostly about climate. But I'm sure you have other applications that you're researching materials for. I just wanted to, I'm interested in, to the extent that you can talk about it.
Yeah.
What other applications do you have in mind right now?
Yeah, so I'll just be very vague about it, but it's like batteries is a great example on which this can be applied, improving the sort of efficiency of batteries, fuel cells, hydrogen fuel cells, water cleaning. And there's even applications which we don't work on, which has to do with generating water out of air. The group out of Berkeley is working on that. Semiconductors, improving materials for semiconductors, but giving them better properties to scale even to smaller bits. There's also lots of coatings being used in semiconductors. Well, there's many more applications, like nuclear fusion, the materials that sort of need to withstand the neutron flux that's being generated in a fusion reactor at very high temperatures. There's a lot of both high temperature and a high neutron flux. And these materials degrade fast under that flux. And so what is the best material to do that? It's a very difficult problem because the physics isn't really understood very well. And actually, I've heard that at ITER, which is the biggest fusion reactor they're making, they started with one material, one metal, and it didn't work. It degraded too fast, and then they had to change to tungsten, which is a different metal. But people don't really optimize it. It's just physical intuition that people use for that. So just very, very, very many opportunities to, once you get a platform like this running, to then fine tune it to different applications. Every application comes with its own complexities, I should say. But then at least you have a head start if you have this platform. And you can quickly get into a super application domain.
Hi, great talk. Thank you so much. I was wondering if in the generative process of new materials or new molecules, is delusional chemistry a problem or not, or if you have to handle it in a way, right? I mean, like having molecules that are not actually, they don't make sense chemically speaking.
We try to avoid those, but so of course we only want to generate molecules which can exist in the actual world, right? So in the end, if something gets generated by the generative model which is not physical, it will very quickly be detected by all sorts of property predictors. So we have a whole stack, a whole battery of property predictors. We look at charge distribution, we look at stability, we look at all sorts of things. We will very quickly fail in this initial property predictor pipeline, and be tossed out. And then we learn about that mistake it's made, and so the generative model gets updated to generate these things next time around.
Right. And what about synthetic possibilities of those? Like maybe the molecule is possible chemically speaking, but it's hard to synthesize.
Yeah, so it's a good point. So we'd like, of course, to innovate and generate molecules which are people may not know yet how to synthesize, but it is synthesizable. But it's quite hard to predict synthesizability. So we are working on it. There's probably things you can't predict about it. Ultimately, you have to go to a chemist, and the chemist will have to come up with a way to synthesize it. But that knowledge isn't very well captured in tables of data, even in the literature, because people only report positive examples and they're very fragile. So sometimes, one lab can do it, the other lab cannot do it. But everything that failed isn't really reported. And so it's very hard to come up with good intuition in an AI sense, good intuition of what is synthesized or not. That is actually a huge problem, I think, in this field.
Thank you.
There was a question in the chat. Whoever is looking at the chat, can you guys read the question? Maybe I can read the question. There's a question in the chat. Oh, yes, here. Do you foresee any ways that scientific AI may fail? One possible pitfall I could see is if the training happens with inconsistently taken data or contaminated or tampered data. Is that a real danger and can we mitigate it?
Yeah. So data is definitely, super important. Now we tend to generate our own data, which means that we're in control of the quality of that data, but definitely, we have to try to grab data from the literature. For instance, I wouldn't say maybe if it's, the biggest issue may be biased data. So like databases are very biased towards certain materials. Let's say, lithium is highly overrepresented in the materials project. Why? Because lithium is used in batteries, right? So this basically means you're looking at a tiny corner and your models are being trained, overtrained on this small corner of material space where you're really interested in another place. If you trust your model too much to generalize away, then that could be an issue, and that's a data issue. So I think collecting data, having large databases, and making sure they cover the space you're interested in well. And if it doesn't, you need to generate your own data, either either in a computer with DFT calculations, or maybe even experiments or robot lab or something. That is the game. I think the machine learning models in the end will be solved, will be easy to reproduce and train, but it's the data issue in the end that is the real moat and the real advantage that you have. Yeah.
How many examples would you typically have in a training data set?
Depends a bit on the problem you're trying to solve. So a property predictor you can do with 1,000, basically order 1,000, or even a few hundred is fine. If you're training a foundation model across all of chemistry for generating molecules, that hasn't been done, you need massive amounts of data. So then you're talking about definitely millions and millions of like DFT, single point calculations. Force fields, maybe, if you train force fields for a specific group of materials, you can do also with less data. So million is nice, but I think a couple of 100,000 is also fine. But it's very important of how narrow do you define your model? Is it one chemical group, or is it all of chemistry? And the other thing which is important is it the property predictor, is it the machine learning force field, or is it the generative model? Also, that factors into it. I think generative models are very data hungry, especially if you do it with diffusion models, because they need to somehow predict precisely how all the atoms hang together from data is that seen. So that's not so easy. So you go from a little bit of information to basically a lot of information, but a lot of possibilities. Where if you do it in the opposite direction, it's more like a classifier or a regressor, and that's much easier to train. So yeah, so I guess my answer is it depends, yeah, I would say if we manage to really get the uncertainty thing under control, then I would say even if you have a model that is trained on few data, but if it understands that it's moving out of its domain and becomes highly uncertain, it's still very valuable, right? I guess the danger is you're training it, you're trusting it. Now you go out of domain and it gives you nonsense. That's the real danger. If it says, I don't know anymore, I think it's fine.
Okay, let's thank the speaker again. finish the photo, so that, you know.
Oh, that was super impressive. Wow. Hang that in my office for sure. Thank you very much. Thank you.
Thank you guys for coming.
I got three.
Great. Thank you so much.
I wonder whether people.
Yes, like this. Yeah. Side. Piece.
No, I mean, like, did they have mathematical or?
Oh, yes, yeah.
So in protein design, when Mr. Roberts was a Nobel Prize winner, he visited protein design.
Yes.
And he said that there is a huge amount of proteins which are well described in the literature that, we don't have any kind of digital model of. And he was looking for almost like a lot of companies to look at all these papers describing all these protein designs that can somehow, put into a digital form so that you can use it to design new proteins for things like drug design or like plastic-based compounds.
That's why I didn't know what to the active.
So on and so forth.
I guess it was time. but-
So I kind of understand it, like, well, this bias.
I always had trouble with thermodynamics, but I don't have a
And
right hand
biology,
these
they have-
expressions. But trying to translate into
They're
something that's
very
visible,
well,
I find very difficult.
like, use everywhere
Yes, yes, yes.
that are not as.
Maybe with the new AlphaFold.
Do you have your stuff? Attached to the office.
Yeah, so I think with AlphaFold, there are probably, now 600 million proteins out there in an atlas. So, and that's probably much easier to cover. But it's not an experiment they do, it's computational, so you can
Right.
cover the space much better. But that's quite new, right? That's the thing.
Yes.
The days, back in the days, it was quite different.
Let's maybe grab our stuff from my office, because we're going outside, so we need to.
Very nice, thank you.
Thank you very much for coming.
Oh. Sorry, my bad.